In the world of materials, we usually choose between brittle hardness or flexible weakness. But nature has engineered a perfect middle ground. The golden silk orb-weaver creates a biological cable that stops birds in flight, combining the strength of steel with incredible elasticity. It does not use industrial heat or toxic chemicals. Instead, it builds this elite fiber through a rapid, liquid crystal phase transition. Inside the spider's spinneret, a watery fluid called silk dope is packed with unorganized, looping protein structures known as spidroins. As this fluid flows through narrowing ducts, the spider's anatomy pumps in hydrogen ions, dropping the pH level to trigger a change. This chemical shift forces the messy proteins to align side by side, transforming them into a highly ordered, liquid crystal state. As the material exits, the spider's pulling force triggers shear-induced crystallization, locking the molecules into a rigid geometric structure. The result is a series of alanine-rich blocks called beta sheets, which interlock through dense hydrogen bonding to create a hyper-rigid cage. These rigid nanocrystals are embedded within a chaotic, flexible matrix of glycine chains that act like microscopic, shock-absorbing springs. When prey hits the web, these elastic loops stretch out, absorbing kinetic impact through molecular friction, while the beta sheets prevent snapping. The web itself is a masterpiece of structural engineering, using rigid radial lines for support and compliant spirals for capturing prey. Under high-velocity impact, the silk instantly shifts its material phase, hardening to absorb peak energy and protect the web's integrity. This localized strain isolation converts destructive kinetic energy into harmless thermal friction, preventing the entire structure from buckling. The spider bypasses the limitations of rigid matter by spinning high-strength materials at room temperature without any industrial solvents. By mastering fracture mechanics and molecular alignment, this small organism outperforms even our most advanced aerospace carbon fibers. It proves that the ultimate defense against the forces of our universe is not absolute hardness, but the intelligent geometry of flexibility.